Okay, so we come to the fifth lecture, which is on the applications of nuclear and particle physics. And these are the areas which we will talk about briefly, namely nuclear power production, how it is very useful in the medical science, uh, how it has been used in agriculture, food preservation, sterilization, and also via radiation-induced mutations. In industry, it is useful in terms of non-destructive testing of various components and so on, uh, large or small. Then it is useful in archaeology and history, for instance, through carbon-14 dating, but there are other isotopes as well which have been used. Then there is geoscience, where there are some advances that have taken place in recent times, and it has a very promising future. And muon tomography. So at present, for instance, you can use cosmic ray muons to do tomography of various objects. So let's come to the nuclear power plant, NPP for short. Nuclear power plants are in some ways coming into vogue because they don't have or they have minimal carbon emission, as opposed to, let's say, those power plants that use coal, for instance. So the basis for nuclear power is the so-called fission reaction, which is the reaction on U-235, U-239, and to some extent in some of the latest reactors, the experimental at this stage, is in 233 uranium. So these are so-called fissile nuclei. So if they capture a neutron, a thermal neutron, for instance, in most reactors, fast neutrons in the so-called fast breeder reactors, then they break up into two parts, roughly unequal parts like mass 90, 100 and mass 140, and in the process you release a lot of energy, like about 200 MeV per fission. That is the amount released, but it also releases neutrons, and these neutrons are more than one. So in principle, this can lead to a chain reaction, and if you can control that chain reaction, then of course you have a running reactor. So in the case of light water based reactors, you have the slowing of neutrons. The neutrons, by the way, have typical energy of about half an MeV, and they have to be slowed down to a fraction of an electron volt before their interaction cross sections become large, or the probability of interacting with these fissile nuclei becomes large. This is slowing down is done with hydrogen in the case of light water reactors, but using deuterium in the case of heavy water based reactors. The energy release, as I said already, is about 200 MeV per fission with emission of about 2.5 neutrons. So you have the extra neutrons to play with, so they can also be used for other purposes. Of course, some of them get absorbed in the material that constitutes the fuel. The neutrons, as I already said, are slowed down by H2O or D2O, actually the proton or the deuteron. Deuteron has certain advantages because it doesn't absorb the neutron with as much of a cross section or as much of a probability as proton, but then you have to separate deuterium, which is only 1 part in 7,000 in normal water. So that costs both effort and money. On the other hand, it is a more efficient reactor once you do that. The neutron economy is much more efficient. The first self-sustaining reaction was achieved by Enrico Fermi in 1942 in a graphite moderated reactor in Chicago. This is a reference which is given there, and the first nuclear power plant was in the then USSR in 1954. It produced about 30 megawatt thermal and about 5 megawatt electrical power. This used about 5% enriched uranium. By enriched uranium, you mean uranium has about 0.7, in natural state has 0.7% of U-235 and 99.3% of U-238. Now this 5% enrichment means 5% of U-235 and 95% of U-238. And this, of course, this first reactor used a graphite moderator. The first commercial nuclear power plant in England was opened in 1956. It used similar enriched uranium, light enriched uranium fuel, but light water as a moderator, not graphite, because graphite in principle can burn, and water is, of course, is safer in that way. It produced 50 megawatt electrical initially, but then later it went up to 200 megawatt electrical. The most advanced nuclear power plants at the present time produce about 1.65 gigawatt electrical of power. Canada developed the first heavy water moderated natural uranium based CANDU reactor, and it was about 200 megawatt electrical in 1960, and India has followed this route. We had a collaboration with the Canadians. The fast breeder reactors use a fuel which contains natural uranium, 239 plutonium, which of course is a byproduct of the reactors that use uranium, because then U-238 can absorb a neutron, produce U-239, and then that undergoes the 2 beta decays to produce 239 plutonium, which of course is a fissile material. And then these fast breeders also use thorium-232, which breeds U-233. These are very compact reactors and use sodium as a coolant to take away the heat, and then there is a secondary channel that generates steam which produces a turbine. The future, I must add, lies perhaps in molten salt reactors that use thorium, apart from, of course, uranium. Okay. Thorium is much more abundant than uranium, so if you make use of thorium, you will breed fuel, and then molten nature of this enables kind of almost online separation of the products that are harmful for both reactor operation and harmful also from the point of view of radioactivity. A big application of nuclear and particle techniques in the area of medical science and technology. So, we of course know, and we have seen in the early lectures, how X-rays have been routinely used for imaging, and now they are very routine. Technology has progressed. We have gone from X-ray plates to films to real-time detectors, solid-state detectors, okay, silicon-based detectors. The latter, these real-time detectors have led to a reduction in the dose, and in some cases even up to a factor of about 100 reduction in the dose that you get because of the sensitive nature of these detectors. The other technique that is widely used now is based on the principle of nuclear magnetic resonance. So, nuclei, in particular protons, which there is a lot of water in the human body. So, the protons have a small magnetic moment, and this can precess in a magnetic field with a so-called Larmor frequency, and that frequency is related to the field through this relation. The frequency is given by the magnetic moment times the magnetic field divided by h cross. And since the human body consists of water, organic matter which has hydrogen, it is the protons which are used. Then of course, you tailor the magnetic field in the MRI device such that you can scan the body by changing the resonant because if the magnetic field is higher, then the resonant frequency is higher, and vice versa. So, there are other techniques as well. So, you can basically image the proton content in a human body, of course, in any other body which contains the organic matter which has protons. And you can get a 3D image. There is another nuclear technique which is called positron emission tomography, which is again based on the fact that if you have a positron emitter, so in beta plus decay, then that positron can get captured by electrons in a tissue, and then they lead to 2 photons, and these 2 photons through this so-called annihilation process, E plus E minus going to 2 photons, they can be detected, and you basically you get one line. But if you have multiple lines, then you can see where they intersect and how often they intersect. So, you can get a map of the places where this beta plus emitter is lodged. And this beta plus emitter is usually, 18-fluorine, which forms part of this fluorodeoxyglucose, FDG. And so this has fluorine 18 has a short half-life of about 2 hours. So it has to be produced in an accelerator, and it can be used for not more than about 10 hours or so, because by that time then the activity has decayed. So the idea behind this is that the cancerous tissue absorbs FDG more than healthy tissue. So this can be used to give a contrast for the cancerous tissue versus the normal tissue and image the cancer affected parts. So this is the typical number, 371 megabecquerel. 1 becquerel is 1 disintegration per second. So this is like 10 to the power of 9 disintegration per second of fluorine 18, and you can do a whole body PET scan using this. For instance, liver metastasis. This is one example of that, where you get a 3D image also. So using software, you can actually, the doctor can visualize where this cancerous tumor is located. Of course, the treatment of the cancerous tissue can also be done using gamma rays, electron beams, protons, alphas, and also indeed heavy ion beams. Heavy ion beams have the advantage that since most of a larger fraction of their energy is deposited towards the end of the range, there is less damage on the intervening tissue between the cancerous tissue and the outside world. There is a new technique which has come by, namely BNCT technique, boron neutron capture therapy, where you get a source of epithermal neutrons by suitable tailoring using accelerator produced neutrons and then suitable collimators and absorbers, and then you can target cancerous tissue again by using suitable compounds of boron, because the neutron doesn't have any electronic energy losses in the intervening tissue. Of course, there is some amount of interaction with protons, but this is smaller than, for instance, what you have in the case of charged particles. And then this boron absorbs the neutron with a large probability, and then the alpha that is emitted in this process, when you have an N-alpha reaction, the alpha basically destroys the cancerous tissue. So this is a very new technique, and this is there perhaps in only 3 or 4 hospitals all over the world. Radiation has also been used in agriculture, food preservation and sterilization, and these are examples taken from documentation of the Bhabha Atomic Research Center in Mumbai, where they have produced mutants to increase the yields of some of the crops. For instance, the classic thing that they have done is to actually improve the yield as well as the oil content of groundnuts, and this is, this was done maybe about 50 years ago, and these groundnuts are widely used in India, particularly in the state of Gujarat, which produces a lot of groundnut. But these mutations, of course, you produce mutations by irradiating, and most of those mutations are useless. Okay, they produce things which are not useful. But there are some mutations which are useful, and then these crops are then selectively multiplied, and they from different points of view, they might be, more resistant to climate changes or to the salt content in water and so on. They may be resistant to diseases that affect crops and so on. So these are examples of, for instance, here is an example of high yield rice mutant, which has been again developed in Trombay in BRC. These are some pictures of fields where these plants have been growing, and then once they are happy with the kind of plant they have, then those seeds will be put out to the general public. Of course, they have to undergo some certification process. The food authority has to approve this, but then once this is done, then this can be used by farmers. Irradiation of food items also takes place, such as potatoes and onions. This increases the life without the spoilage. So it can last for almost like a year or 2 years. In the case of spices and fruits such as mangoes, this is a requirement because it kills harmful microbes. And some countries like the US, Europe and so on, there is a requirement that these spices and fruits be irradiated. And of course, the dose is decided by, it should not do too much damage to the product, but at the same time it should kill off the microbes. Electron beams of a few MeV has been, for instance, used to treat sewage in Ahmedabad. There is a big plant that does that, and then the treated sludge is actually sold as good quality soil to farmers. So this is, for instance, the radiation processing plant that BRIT runs in Vashi, is a suburb of Mumbai, and this is the plant in Lasalgaon near Nashik in Maharashtra, which irradiates onions basically, and makes them last for a much longer time. Otherwise, you have fungus attacking the onion, and then its life is decreased quite a bit. Nuclear techniques, of course, are used for non-destructive testing. X-rays, gamma rays, neutrons are used for radiography, for instance, for visualizing welds, inner parts of pipes, critical parts of space missions, even nuclear reactors. And these probes complement ultrasound. The portion that scatters or absorbs more of these probe particles shows up as darker areas on a film or even a real-time detector placed behind the object which is under scrutiny. Apart from imaging, of course, there are also other techniques such as the phase contrast technique, where you use the phase of the scattered particle to improve the sensitivity in imaging. Similarly, radio tracers in fluids help identify leakage spots, because these radio tracers then leak out of the spots, and then you can count that radioactivity. It can also be done in flow loops of in the chemical industry and so on. It can also help identify partial complete blockages and quantify flow rates, for example. For instance, this is used also in human beings to find out how fast the blood is flowing in arteries and veins and so on. The sources of X-rays, of course, are the X-ray tube, but also Bremsstrahlung radiation using electron accelerator. Sources of gamma rays are cobalt, iridium, and 137 cesium. Of course, there are advantages in using Bremsstrahlung radiation because the electron accelerator can be switched on and off, whereas the radioactive source can't be switched off. There are sources for neutrons that are used for either nuclear research reactors or the DT reaction, which is accelerator based for producing 14 MeV neutrons. So this is a neutron radiograph of a jet turbine blade, and these are photographs using neutron phase contrast imagery. So this is the original phantom, then the low contrast, high resolution, high contrast, low resolution, and finally the neural network enhanced image using phase contrast methods. It is used in archaeology, for instance, to using mainly carbon-14 dating. Of course, there are other isotopes as well that can be used. So this was developed by Libby, and this is the key paper for which also he got the Nobel Prize, the Chemistry Nobel Prize in 1960. So the principle is that life forms exchange carbon dioxide from the atmosphere when they are alive, but this exchange stops when they die. Okay, so natural carbon has carbon 12 and carbon 13. Carbon 12 is 99%, carbon 13 is 1%, but there is a very tiny amount of the order of 10 to the minus 14 per carbon 12, which is produced in cosmic ray interactions with atmospheric nitrogen. So then it gets into the carbon dioxide cycle, and that is what undergoes exchange with life forms. By counting the carbon 14 either through its beta decay, so the half-life of carbon 14 is 5,700 odd years. It's a low energy beta, so the continuous spectrum which with the endpoint energy of 156 keV. So let's say the average energy of the order of 70-80 keV or 50 to 80 keV, and so you measure either the decay in liquid scintillators in a very low background setup, and then you can date the. So you basically, if you know the carbon 14 content, then you can date an object between about 500 years to 50,000 years. Of course, instead of measuring decays, you can also count the carbon 14 itself. This greatly increases the speed and accuracy of the dating. So this is done using either tandem machines or very recently ion source based and ion source plus charge exchange using negative ion of carbon 14, and that is used to measure the carbon 14 itself, and this can be used to see the reduction from the normal ratio, which is 10 to the minus 13, whether it goes to 10 to the minus 14, 10 to the minus 15, and so on. So, the reference for the accelerator based mass spectroscopy, where you count the carbon 14s, is this 1980 reference using a tandem accelerator. As I said, the other method using ion source we perhaps might discuss sometime later. That is a very recently developed method, maybe of the order of 5 years ago. So, the mass spectroscopic method of counting is based on the fact that the other isobar which can lead to contamination, 14 nitrogen, this is not possible because it is not a stable negative ion. Okay? So, there is no basically contamination when you are detecting carbon 14. They can only be scattered particles and so on, or some impurity in the detection zone, and but those can be easily identified and removed. So, there are these two methods which is basically produce carbon negative ions and negative ion source, inject into a tandem, mass analyze the accelerated beam for carbon 14 after, of course, stripping the electrons in a stripper in the tandem high voltage terminal, and then identify and count ion by ion. The other way is you can produce an intense beam of carbon, positive ions of carbon, do a charge exchange to get carbon negative ions, and then mass analyze using a magnet. The advantage, of course, this is a much more compact device. You can also prepare the sample. You don't have to prepare the sample as is required by the negative ion source here. You require to graphitize the source, and that is an expensive and time consuming process. It can be done, of course, but this, in the case of the ion source method, where you do a strong positive ion beam and then you do a charge exchange, there you can very easily make carbon ions in the let us say an ECR source. You just burn the carbon to get carbon dioxide, and that you feed into the positive ion source. The voltages are also lower, whereas here it is of the order of millions of volts, here it is of the order of 100 keV, and because it is a more compact and more reliable device, you have higher sensitivity and accuracy. I will give two examples of carbon 14 dating, namely, so these are some of the references for the second method. The references of the examples are the so-called Iceman Otzi, who was about 4,500 years before the present, and the Turin Shroud, which is only about 700 years before the present, not 2,000 years present, at least from the sample that was from which the carbon 14 dating was done. So, these are just pictures. This body was found in the Alps, very close to this Switzerland-Italy border, and this work was done in 1991, radiocarbon dating of Iceman Otzi, and a lot of detailed work has been done, not just dating the sample, but also what was there found inside of the body, the food, the other things that he was using, and so on. In fact, there is a museum dedicated to this Iceman Otzi, I think in Italy. The Shroud of Turin, of course, which is supposed to have been part of the attire of Jesus Christ, was in Turin, and the faithful people used to go there, and so it was mooted that why can't one date this Shroud of Turin, and so this was done, and it turned out that at least from the samples that were given by the priests to the scientific community of dating people who dated using the accelerator mass spectrometry, it turned out that it is only about 700 years before the present. Of course, there is still a controversy saying that maybe these samples are not the right ones, maybe there are other samples should have been taken, and so on. Okay, in geoscience, for instance, measuring the time evolution of water bodies using the radioactive isotope tritium on a time scale of the order of 100 years, or chlorine 36 on a time scale of 1 million years, these have been used. And what they use is the bomb pulse, which is a excessive production of these two isotopes in the thermonuclear tests of the 50s and 60s, in order to measure the ratio of tritium to helium-3, because this is the decay product of tritium. Hydrogen-3 decays to helium-3. And chlorine-36, of course, produced through neutron absorption, and chlorine-35, which is an impurity in water, also is produced. I mean, there are other things that produce chlorine-36 through spallation reaction of cosmic rays, 40 argon, 39 potassium, and so on. Also as waste from nuclear reactors or nuclear reprocessing plant. Tritium is measured using a cocktail of tritium and liquid scintillator, and counting the very low energy, because the endpoint energy is only 18.5 keV. So you have to count very low beta particles in the low background setups. Alternatively, this can be measured in older samples, and of course, chlorine-36 have been measured using accelerator mass spectrometry. So the other thing where such a thing is useful in geoscience is prospecting for uranium and thorium ores, using various methods like GM counters, then more sensitive scintillation detectors to measure the gamma ray background. Then in nuclear waste storage, for instance, you can concentrate this activity and then put it in suitable deep sites where the long-lived isotopes can remain in glassy forms, and then again putting it in a stainless steel container and so on in seismically safe sites. In future, perhaps we will be able to transmute this radioactivity using intense high energy proton beams through using this spallation reactions and produce more harmless isotopes. But this, as of now, is not still a practical technology. It has been shown in an experimental way, but in order to be practical, it has to be also, there are other financial and other considerations. There is also a futuristic possibility of doing neutrino tomography of the Earth, and the early steps has been taken using the attenuation of multi-TeV atmospheric neutrinos. This has been done by the ice cube detector, where they measured the mass of the Earth using weak interactions. But in principle, you can do tomography of the Earth, which is supposed to be a mantle, and then at the center you have a core. So using a detector such as ice cube, you can measure these neutrinos, and not just the attenuation. You can also use other effects like neutrino oscillations, and these will probably be the future of neutrino tomography of the Earth. There is also this area of muon tomography. Muons, as we know, are very heavier cousins of the electron. They interact electromagnetically and through the weak interactions, and typically they have a range in matter of 1 GeV. Muon has a range of about 500 gram per square centimeters, and cosmic rays are, they come at all energies from hundreds of MeV to TeV and even higher. Okay, so these muons were discovered in cosmic rays, and they shower at the rate of about 200 muons per square meter per second. This should be second inverse. There is a mistake here. Traditional tomography uses X-rays, neutrons, NMR, and so on, PET scans. Whereas if you use cosmic rays, you don't have any radioactivity at all. You're using just natural cosmic rays. And this has been used, for instance, to scan large size objects such as containers in ports, but also nuclear reactors, pyramids, and volcanoes. How does it work? The principle is the following. Muons undergo small angle scattering, which depends on the atomic number of the material. Okay, so the small angle scattering is more if there is a higher Z of the material, and less if there is a smaller Z of the material that constitutes the scanned object. So you have to basically track the muons before the object and after the object. So these are examples of muon tomography of Fukushima nuclear reactor. You know that there was an accident in Fukushima, so muon tomography was used to find out how is the core doing, whether there are any voids, and indeed they found voids and so on. It has also been used to tomograph voids in the pyramid, this particular Khufu pyramid, where if there is a void, then in that direction you observe a small excess of muons. Okay, so you can then do that in 3 dimensions, and you can locate the void. Okay, so in summary, I should say that all advances, almost all advances in basic sciences such as nuclear and particle physics, have applications in various areas. They may not be visualized as such when these advances took place, but in the course of time, a technology develops, and then that is used, that is very often useful in other areas, not just nuclear and particle physics, in areas as we saw, agriculture to geoscience to medicine and so on. And these are some of the areas which we have given examples of, or we have seen examples of: power production, diagnosis, treatment using radiation, developing new varieties of agricultural species, to tomography of large entities, to dating of objects and bodies of historical and archaeological interests. Thank you.